So for a normal mode, we just found that the space variation part has to solve the equation of motion for a simple harmonic oscillator, the standard one we've been solving over and over again. So we don't have to solve it again. We know the answer. The answer is a sinusoidal function. So we will write down our f of x as a sinusoid. We don't know the amplitude. We'll give it some arbitrary amplitude. Sine, the frequency was set by that equation of motion. It must be omega, the frequency, over the speed v. And we don't know the phase, so we'll put plus phi, arbitrary phase. So the way we get these constants that we're putting in, just like before, is from boundary conditions. So when you're talking about a simple harmonic oscillator, you call them initial conditions because they're boundaries in time, right? Something of this time and something at that time, boundaries in time. When you put them in space, in this case we've clamped both ends of the string, usually it's called a boundary condition because it's more of a spatial thing. Mathematically they're the same. You can have conditions on the time, on the x, and conditions on t. But the boundary conditions we have are that the ends of the string are clamped. So one we can write is that f, you could write it like this, f of 0 and t. That means f at x equals 0 for all time. Right? F of 0t equals what? 0. It's clamped at f equals, or at x equals 0. We could write another one, f of L and t. So at the other end of the string, it's also clamped. At all times, it's clamped at any t, and it's 0. Because we put a 0 in the function for y of f times that cosine is still going to be 0. Right? So this will drive y to be 0 if f is 0. So let's look then at this and plug in these boundary conditions. Let's see. So if we have f of 0, that's going to be a sine, and this is going to be 0 plus phi. So the x part is 0 equals 0. So how can that be 0? Well, we don't want the amplitude to be 0. That's a trivial solution, not very interesting. So sine phi must be 0, so phi must be 0. And this isn't too surprising. It's a clamped string. The ends have to be at 0. We used a sinusoid. Sinusoids like to be 0 at 0. So it's not too surprising the phase came out to be 0. Let's look at this boundary condition at L. F of L equals a sine, and then we have omega over VL. And we already said the phase was 0, so we can ignore the phase, equals 0. Well, how's that going to be 0? Well, you could say, well, then omega over VL has to be 0. But that's not very good because then that means the frequency is 0. That's what we're finding here is the frequency. And the frequency being 0 is a solution. It's just kind of a trivial, boring solution where the string doesn't move. Right? So we don't really want to consider that solution. What we really want to look at is other times sine could be 0. Right? It's not just at 0 here. It's also at pi. Right? Sine of pi is 0. Sine of 2 pi is 0. Sine of 3 pi is 0. Sine of negative 47 pi is 0. So sine of n pi is always 0. So what you could say is that omega over VL has to equal n pi, where n can equal 1, 2, 3, etc. N can basically be any integer. N equals 0 is kind of boring. Okay? So now it may bother you that here we said, I'll just call it 0, and here we let it be equal to n pi. Right? And it's mathematically a little bit arbitrary, but basically you can imagine if you're moving along a sinusoid, which point along the same frequency, along the same wave you define as 0 doesn't really matter. When we're doing the simple harmonic oscillator descriptions, picking different n pi's to be 0 and something like this would have just been starting time at different points. It doesn't make a difference. So since it makes no physical difference, here we just say the phase is 0. Here, we're going to see it does make a physical difference. What this is saying is that if that's true, that normal modes only exist at certain frequencies. Okay? And those frequencies are, we can solve this and see what omegas work omega equals, let's see, it's n pi over L times V. So we can write a subscript omega n, because these are all the omegas, all the frequencies at which a normal mode really does exist. So you can put a 1 here, and it's pi times the velocity over the length. You can put a 2, 3, 4, etc. All these higher and higher frequencies. And this also illustrates you got to keep up with what's a property of the system and what are we looking for and what have we already found, you know, all these things. When we're talking about the simple harmonic oscillator, omega was a property of the system. It was a square root of k over m. But now we've done something else. We've said, let's guess a normal mode solution. And let's guess that it can go at some arbitrary frequency, some drive frequency omega. So we actually have never set omega here. We never said what omega had to be. We said if there's some driving omega, some normal mode at omega in time, it affects the spatial frequency, but that never really told us some real value that omega had to be. So it wasn't until we plugged in this boundary condition, it didn't tell us the amplitude, it actually told us omega. It makes sense the amplitude can be anything, almost all oscillations, the amplitude is always free. But we ended up with a phase being 0 and having a specific omega. And this time not a single specific omega, but a whole set of omegas. But it's not continuous, only to certain omegas does a normal mode solution actually work to solve the equation.